The third part of the course on the Nadca 207 specification for die casting dies will focus on tool design and manufacturing. In this Nadca 207 course block, we'll show you how to prepare die casting dies to survive high-speed quenching and how to avoid mistakes that could compromise our effort to produce a die with maximum thermal fatigue performance. At the same time, we will show how individual parts can be classified in terms of heat treatment and testing, so that die production is not only reliable, but also economically viable. This classification of parts will subsequently enable the die-cast foundry to selectively work with them, from the point of view of the traceability of maintenance operations or the production of spare parts. However, it is also necessary to realize that the CQI 27 directive from the Automotive Industry Action Group, entitled Casting System Assessment, applies to die-casting foundries with production for the automotive industry, where in Table H, Point H 1.7 and H 1.8, the obligation of pressure foundries choose die materials according to Nadca 207 and perform heat treatment according to the same standard. In the first part of this course, we will first explain certain geometric or technological standards that must be met so that mold inserts are not damaged by stress cracks during hardening. This is very important because, as we have already said in previous courses, to achieve the correct internal structure, the cooling rate takes precedence over deformations. And since rapid cooling also brings with it high internal stresses, we must follow certain rules in the design and manufacture of inserts so that individual dies are not damaged before they are completed. The other part of the problem are thermal fatigue cracks. In order to postpone their appearance on the die as much as possible, we must adhere to the rules described in the previous courses. The die's design itself should also adhere to the recommendations from the Nadca Product Specification Standards for Die Casting publication. This document indicates how in practice to ensure the production and quality of key inserts in relation to the Nadca 207 specification, and its classification of heat treatment in Class 1 and Class 2 quality. At the same time, it proposes a solution for the traceability of individual parts of the die when using the mold in a pressure foundry, as from the point of view of wear and tear, as well as the need for spare parts. The goal is not only to produce a quality tool, but also to control the costs that we had to spend on this quality. These should also include the costs of maintenance, service, or the cost of manufacturing spare parts, all related to the lifetime of the individual parts of the die. The result should not only be detailed information about the lifespan of individual parts of the die and their wear and tear, but above all, documents for specifying a new duplicate tool with corrections according to previous findings, and with the possibility of their financial valuation for determining the price of a new tool. As previously stated, die-casting dies come in a variety of sizes, shapes, and weights. Regardless of this uniqueness, it is necessary in all cases to ensure high-speed quenching, guaranteeing the correct structure, with maximum impact strength. During the heat treatment process, the parts are subjected to stresses, both tensile and compressive, which originate from the temperature difference between the surface and the core of the part, and from the transformation of austenite into martensite during hardening. Hardening cracks then appear in areas where the maximum tensile stresses are located. We will show which areas they are next. But it must be said that in order to achieve good impact strength results, the speed of cooling is an absolute priority, and therefore the heat treater must cool as quickly as possible, regardless of possible distortions or cracks. It is therefore up to the designer to treat the shape of the inserts to survive hardening. During heating or cooling, stresses are generated inside any body that is in a solid state, due to thermal expansion of the material. These stresses are proportional to the modulus of elasticity of the material E, and to the proportional change in dimensions epsilon. The greater the temperature difference between the core and the surface, the greater the difference in the expansion of the material inside the body and on the surface, and thus the greater the tension. In practice, we can interpret this as the faster the heating or cooling, the greater the temperature difference, and the greater the stress inside the material. The picture shows a model of a mold base measuring 600 by 400 millimeters, on which the state of stress was modeled during cooling from temperature of 1050 to 50 Celsius. Since the most dangerous source of cracks are tensile stresses, we focused on these stresses during the analysis. From the figure, it can be seen that the critical areas are around the notch, and at the same time there are other areas on the periphery of the mold base, lying outside the proper cavity. This is very important because the designer concentrates on getting the cavity shape into the die correctly, and the auxiliary shapes on the periphery are usually no longer important to him. On the stress model, the stresses in the notch area were compared when the notch is made without a radius, and when the radius was 10 millimeters. The image raster represents the computational network. The initial state at a temperature of 1050 degrees Celsius is shown in blue. The final state is shown in ochre color. A comparison of both shapes shows how the plate deforms during cooling. It can already be seen from this illustrative example that deformation-free processing we cannot expect. The reason is the phase transformation and volume change from austenite to martensite, and at the same time, the stress resulting from the temperature difference. In the case of a notch with a radius of 0, a maximum tensile stress of 1,120 megapascals was identified. In the case of a notch with a radius of R10, then 770 megapascal. So the stress dropped by only 31%. So what does this mean? If we want to prioritize small deformations over the structure, and we want to cool slowly during quenching, we will still not achieve a deformation-free state, precisely with regard to the above. It therefore makes sense to prioritize achieving a quality structure and to cool during hardening as quickly as necessary, regardless of distortions. The parts will be deformed as during slow cooling, although a little more, but we will have guaranteed mechanical properties. This is what we primarily need. We just have to avoid catastrophic gross cracks. This figure shows the dilatometric curve of the change in the size of the crystal lattice during heating and cooling. During heating, due to increasing temperature, the volume of perlite increases up to the point of transformation to austenite. In the next phase, the austenite lattice increases until the austenitic temperature is reached. During quenching, the austenite shrinks as a result of the temperature drop, up to the martensite start point. Here, a critical period occurs when the transformation of austenite into martensite leads to a significant increase in the volume of the structure. For individual structures, untempered martensite is larger than tempered martensite, which is larger than bainite, as well as ferrite. Austenite reaches the smallest volume. If there is a superposition of stress from the temperature difference and from the martensitic transformation below the martensite start line, and at the same time it is in the area of tensile stress, there is a risk of cracking of the part. However, because due to the structure requirement, cooling must not stop at the martensite start line, we must deal with this problem primarily by ensuring that the shapes of the die will provide as minimum areas with potential concentration of tensile stresses as possible. This is mainly solved by sufficient radii. The radius R0 is practically inadmissible, the radius R3 is minimal, and the radius R10 means the safety of hardening. In the last phase of cooling, we slow down cooling even more by removing the die from the furnace at a temperature of core equals 100 degrees Celsius. The cooling up surface equals 50 degrees Celsius we provide out of the furnace on the cooling station, but the designer may no longer be interested in that. Its only requirement is a good structure and required hardness. On this picture, we are already getting to practical examples. In the theoretical model of the impact of the notch on stress, it was seen that the crack spreads from the sharp corner of the notch at an angle of 45 degrees further into the body. This is a consequence of the superposition of tensile stresses in the x direction and in the y direction. In a practical example, it can be seen that the agreement between the model and reality is very accurate. A similar case is also in this picture. On the outer part of the pad for the tool for extrusion of aluminium profiles from the steel 1.2714, the designer drew a groove for fixing the position of the pad without the necessary radii. As a result of the concentration of tensile stresses at the point of the notch, the pad cracked. The crack stopped at the center hole for this part, weighing almost 200 kilograms. In this example, it can be seen that the maximum tensile stresses during hardening occur not in the center of the die, but at its periphery. In this case, the designer built in the inlet gate close to the periphery. The thin wall bridge of the material was torn during hardening due to tensile stresses. Only because the hole was through did the crack cause no further damage. Otherwise, the entire die, weighing more than 300 kilograms, would probably be destroyed. In this case, the designer was not so lucky. As this was a heavy piece, a crane eye hole had to be added to the back side. Its location is in the photo. At the place of the threaded hole, a crack appeared between the hole and the periphery of the body. Since the insert was made of H11 unremelted steel, with many impurities, with a gross austenitic grain, size 4 and 5, the material's resistance to crack propagation was significantly reduced. Since the opening was blind, the crack did not stop as in the previous case, but spread through the entire body to its center. The piece was completely destroyed. From the point of view of use, the designer could have drawn the hole for the crane eye anywhere else. If we are able to model or estimate the orientation and value of stresses during quenching process, then the following solutions can also be applied. The body, in the place where there may be potential cracks or deformations due to high tensile stresses, is cut where it does not bother us technologically. The resulting effect will be similar to the through hole in the already shown example, eliminating all potential tensile stress concentration points. Although in this case it is a mold for plastics, for car headlights, and the cooling rate during quenching was significantly reduced, the insert was completely destroyed. The crack propagates from the sharp corner in agreement with the model. The missing radius in the groove on the periphery of the body is a significant risk for hardening. The quality of the material also contributes to the spread of the crack. When after a metallographic examination it was found that grain size 2 to 4 does not correspond to the specification, for example, grain size 7. Despite the fact that it is a massive piece, the body cracked right up to the center of the insert. This image shows an example from Kind & Company, where a heavy die cracked where the cavity insert is passing to the parting plane. Missing or small radius means high tensile stress during cooling. It is with this example that steel supplier Kind & Company shows why the minimum radius should be at least 3 millimeters. However, it must be said that a crack will only occur if the maximum tensile stress exceeds the strength limit of the material. So, there is a clear relationship between quality die design and quality steel. The repairability of such a crack is debatable with respect to the through cooling channels. The pictures show typical examples of parts for hardening with mandatory radii of at least R3 millimeters. In the production of different inserts, cooperation between the designer and the tool manufacturing technologist is needed. In this case, although the designer could have thought of radii, the machining method created a number of notches, resulting from the inappropriately chosen distance of the drilled holes and the machining method. As a result of this choice, there are a number of places where a crack can be initialized. It is also necessary to remember this when preparing the insert for hardening. The most extreme case of such a crack in practice is a crack where the stress concentration was initiated by embossed letters on the plate periphery. In this case, the designer chose a drilled hole, probably for the ejector pin, that touched the cavity and creates a thin transition wall on the die. As this thin wall cools first, tensile stress develops in it, leading to the formation of a crack. If it is not possible to move the ejector pin hole further from the cavity, it is better to make this hole after hardening. It will be more expensive but safe for heat treatment. Another case of drilling holes. Again, thin burrs after machining can be the source of cracks. Before hardening, it is necessary to remove the listed defects manually or by additional fine machining. Here is an example of drilling cooling channels. Since the transition wall cannot be ruled out from the point of view of the dimensions of the plate and the dimensions of the cooling channels, it is necessary to think about the fact that it must be treated before hardening. Otherwise, due to the concentration of tensile stresses on the outer side of the plate, the parts may crack here. This picture shows a hot forming tool. The cooling channels are close to the surface and have the task of cooling the surface so intensively that the formed sheet hardens. Their number cannot be reduced or the holes cannot be moved further from the surface. Therefore, there is a great risk of cracking during hardening, especially if sufficient attention is not paid to the machining of the thread. The thread is only used for screwing in the cooling channel cover and has no other significant function, but the thread is a source of notch stresses. One of the possible solutions is to produce the thread after hardening by EDM, but it is necessary to pay attention to the EDM parameters because the remelted layer in the thread cannot be removed. The machining method, choice of tool, chip thickness, and other parameters are also important. With a surface prepared in this way, it is obvious that basically every trace of the milling cutter can mean a notch effect with a concentration of tensile stress. Since today, the majority of processing is solved digitally in graphic design software, with subsequent data transfer to CNC machining centers, it is not a problem to ensure a simulation of the result and correct the program even before the actual machining is carried out. In this picture, for example, there is a proposal for machining burrs and chamfering sharp edges in the CATIA program within one clamping. The resulting effect is here. A special case is the application of electro-erosive machining. It is known that due to an electric discharge, a thin layer of remelted material is formed on the surface. It is brittle and hard and can be a source of cracks. If EDM is applied before hardening, the layer must be treated at least by annealing to remove stress, but even better by soft annealing or annealing with recrystallization. In the case shown in the picture, this was not done. Moreover, the shape has sharp corners with 0 radii. Cracks after hardening are the result of the fact that the layer was not removed and annealed before hardening, and that the shape was made finished without radii and necessary additions. The designer should also think about this situation and mark on the drawing the places machined by EDM and the places from which the remelted layer must be 100% removed. It should also indicate whether EDM is performed before quenching on the annealed material or after quenching. The technologist should then determine when and what kind of annealing process will be included. If EDM is applied after hardening, which is the preferred option, then after EDM, the layer must be manually or mechanically removed and then annealed. Otherwise, it will be a source of cracks during cyclic stress from thermal fatigue. A similar problem is represented by welding. It is used to correct a faulty machining process, or to change the cavity after testing to achieve the correct dimensions of the insert. Therefore, this process cannot, with exceptions, be predicted in advance. For welding before quenching, a different procedure and electrode is needed than for welding after quenching. If we really have to weld, then the insert needs to be preheated to a temperature above martensite start, optimally 400 to 500 Celsius, and then annealed to remove stress. If this procedure is followed, it is possible to obtain a weld with material properties close to those of the compact die material. If not, then it is the source of catastrophic cracks. Recently, the application of controlled oxidation of the die surface has been significantly expanded. The layer of iron 304 oxides helps to cool the die surface by better absorbing the lubricant. This surface treatment should also be prescribed on the drawing. So now, let's summarize. In order for the die to have the correct structure, they must be hardened with a maximum cooling rate of at least 28 Celsius per minute. In order not to crack during this high-speed cooling, they must have a suitable shape that allows them to survive the maximum tensile stresses that arise during the heating and cooling process. For die casting dies, internal structure takes precedence over minimizing deformation. The minimum requirement is to apply the R3 radius wherever tensile stress concentrations may occur. But the 10 radius is safer. In order for this to be implemented in practice, it is recommended to create a special process drawing for the machining of the die for quenching. The method of machining before hardening should ensure adequate surface quality so that there are no places with notches, generating possible high tensile stresses. The designer should also take into account the positions of the individual holes for the ejector pins in relation to the cavity itself, so that there are no significant transitions in mass. Special attention should be paid to the threads on the periphery of the insert. The shapes must be cleaned of burrs, the outer edges should be chamfered. All risky transitions between the holes and the cavity should be treated. All points of potential concentration of tensile stresses must be removed. Massive inserts must have holes prepared for placing thermocouples, especially T-surface. Where EDM machining will be performed, the designer should prescribe the locations where the remelt layer must be removed. If the rules outlined in the previous slides are applied, we are very confident that the die inserts will have the required properties while surviving high-speed quenching. They will therefore have good prerequisites for high resistance to thermal fatigue. But that's not all we have to do with die preparation. Even before we proceed to finalize the drawing documentation, we should check that our expectations will be met. Today, there are a number of software tools that simulate the process of injecting the melt into the die. These examples are simulations from the ProCast program. The video on the left shows a simulation of the temperature distribution in the mold during melt injection. The video on the right shows the temperature distribution during cooling product in the die. From such a simulation, it is possible to judge the critical points of the die and then modify them. A similar procedure can be followed when simulating heat treatment. This video is simulating heat treatment process by software named Deform. On the left is the simulation of the martensitic transformation during quenching in the part, and on the right is the stress analysis. If in doubt, there is still time for change. If everything is okay, and we are sure of the design of the die, in the next phase of preparing the drawing documentation, we should start applying the principles of recommendations according to publication Nadca Product Specification, Standards for Die Casting. These will help us to better specify the requirements for the individual parts of the die, enable their planning during production, ensure the necessary quality, and at the same time will serve as a basis for the traceability of parts in the die casting foundry. So once we have the assembly of the die, we should specify its individual parts according to their function and expected lifetime. An illustrative example of how to do it is on this sketch. In addition to the categories mentioned above, a third one needs to be added, which is the categorization of heat treatment according to Nadca 207, specified by the terms Class 1 and Class 2. With this categorization, we distinguish individual parts of the die according to the method of testing the quality of the input material and the quality of the heat treatment performed. This creates something that we can call the die birth certificate. It contains an inventory of all parts of the die, their brief description, categorization according to various criteria, production costs, or the lead time required for their production. Categorization of heat treatment testing according to Nadca 207 is important as well. We have to classify the parts by Group Class 1 or Class 2. This die birth certificate can take different forms depending on the tool shop. In our case, the following fields are listed in the table. In the field Insert Name, we specify the insert specification, production and serial numbers, steel grade, heat treatment prescription, and required hardness. The source field indicates whether the part is manufactured or purchased. In the categorization section, the classification is given in terms of the functionality of the part in the die and its expected lifetime. Again, it depends on the tool manufacturer how they prepare these classification lists. In the other fields, there are data on the costs of the manufacturing, the production or purchase lead time, and the heat treatment group according to Nadca 207. In our case, 3 categories are listed. Class 1 means that it must undergo all inspection operations according to Nadca 207, points A to J, including toughness tests. Class 2 says that all checkpoints A to J according to Nadca 207 are required, but no impact testing is performed. Therefore, coupons are not needed for the production of impact test specimens. On the other hand, the tool shop, in order to be able to perform tests A to J without I, but above all, to be able to check the input properties of the steel by comparing the input quality according to the Nadca 207 maps for annealed structures, must take a sample of the material in another way. How? That is at the individual discretion of the tool manufacturer. But if the designer thinks about it from the beginning, as soon as he categorizes the die parts, he can mark the sampling point directly in the drawing. An example is this procedure, where 3 pins are made on the backside of the insert. One serves for quality control at the entrance, the second for quality control after heat treatment, and the third remains on the insert for possible future assessment in the die casting process. There is one more category that is not described in Nadca 207, and which I refer to as Class 1 with an asterisk. It is a case where we cannot perform impact tests for time or economic reasons, but at the same time we want to have witness material in case of a future claim. So we order the material with the additions to the coupons, but we don't test these coupons. We just store them in the archive. In case of tool failure, we can return to the input test at any time and verify the capabilities of the input material. The finished tool, with complete accompanying documentation, is handed over to the die casting plant. The birth certificate of the die is then used to record the use of the tool with an emphasis on the date of use, on the number of shots, on the state of wear of the parts, or on the record of the spare parts agenda. However, it should also record other data that is required by CQI 27, Table H for die casting plants. The picture shows an example of the record of the production of the die for a certain period of time. The pressure foundry monitors and replenishes the number of produced pieces. The end of life of individual parts of the die, as well as their replacement. As we require traceability of each part, even new ones, spare inserts or die parts must be registered under the new version. This applies to both manufactured and purchased parts. Of course, the form can look different. It depends on the tool manufacturer or the die casting plant. But it must give an overall overview of the service life of the die parts and the manner of their wear, or the reasons for the end of their service life. This is important both for recording costs and for planning duplicates. In parallel with the form for the traceability of individual parts of the dies, there should be other records where all other service interventions will be recorded. The time data on the application of the die to the machine and its shutdown, information on the condition of the final product, with tracking of the costs of additional processing, machining or other, often also additional control operations. There should be records of internal or external defects as well, or data on the machine on which the production was carried out, and the consumed electrical energy related to this production. In this case, the example of the birth certificate of the die is therefore only a simplification of the entire very complex system of tracking the high-pressure dies and its products. Only with detailed, statistically evaluable information can we subsequently draw conclusions about the lifetime of the tool and take corrective measures for their maintenance or for the production of new dies. The course material selection and testing is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a perpetual license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0, on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system, LMS, that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, So I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.